100 years ago, the science community, led by Albert Einstein, predicted the existence of gravitational waves, a ripple in space and time. But we couldn't see them. We couldn't measure them. We couldn't prove that they were until that one moment in September 2015. The first signal. 0.2 seconds, captured by the LIGO detectors in the United States. Gravitational waves that shot through our Earth were translated into sound and image, a tiny signal, but the proof was finally there. We in the Netherlands, Belgium and Germany, together with our host of partners, can deepen our knowledge of gravitational waves thanks to the Einstein Telescope. The detector can measure up to 10 times more accurately and tell us more about the true nature of black holes, neutron stars, and even the universe in its early days, just after the Big Bang. To develop and build the telescope, we need state-of-the-art technology that will stimulate and bring together science and industry in the 3 countries, especially in the Euregio Meuse-Rhine. The Einstein Telescope will put our countries in a unique position, enabling us to achieve a globally leading position in a pioneering field of science. Our 3 countries, and the Euregio especially, will benefit enormously from the huge scientific, economic, and social impact. The Einstein Telescope, an opportunity for the Netherlands, Belgium, and Germany, an opportunity for humanity.
Good afternoon, everyone, and a very warm welcome to this first edition of the Einstein Telescope Industry Webinar Series. My name is Euregio, and I'll be your host today as we kick off what promises to be an exciting journey into one of Europe's most ambitious scientific and technological endeavors of this day and age. As you just heard in the opening video, Einstein Telescope will not just be a leap forward for gravitational wave research. It's also a unique opportunity for innovation, collaboration, and regional development across industries. As we look ahead to its realization, the role of industry is not only vital, but central to making this vision a reality. Therefore, this webinar series is designed to open the dialogue between science and business, to explore where opportunity meets expertise, and over the upcoming webinars, we'll be bringing together voices from across sectors to dive into key themes from advanced engineering to sustainable construction, from cryogenics to data science and everything in between. But we'll also bring you the latest news on any new calls, general developments around Einstein Telescope, and results achieved in the R&D projects that are already underway. Today, I'm thrilled to welcome 3 distinguished guests who will bring deep insights and perspectives from their respective fields. Marion Purio from FAF Aachen, Remy Wielands from Milan's UMPT, and Jochem Klaassen from Lionite. Together we'll set the stage for the road ahead, exploring how companies can engage, contribute, and benefit for the development of the Einstein Telescope. So let's get started. Now, when you hear the words Einstein Telescope, your first thoughts might be black holes, galaxies, and gravitational waves. Very fascinating, for sure. But what's just as interesting, or I should say even more relevant for those of us in industry, is that the Einstein Telescope is not just a scientific milestone. It's also going to be a technological and industrial accelerator. And whether you are a business leader, an innovator, a supplier, or an entrepreneur, this project might just change the future of your sector. So let's break it down. Starting with the instrument, the Einstein Telescope, or ET for short, and trust me, I will say this abbreviation a lot today, will be Europe's next generation gravitational wave observatory. A complex instrument designed to be 10 times more sensitive than existing detectors, therefore capable to unlock data from the deepest corners of the universe, from just moments after the Big Bang. It's an ambitious infrastructure, built roughly 250 meters on the ground, in a triangular shape with 10-kilometer arms, containing ultra-high vacuum tubes, cryogenically cooled mirrors, and laser interferometry that demands nothing but absolute precision. A massive gain for fundamental physics, but with its unique requirements, also a game changer for high-tech businesses. Not just because it requires technology that doesn't exist yet, but also because the engineering challenges of ET touch on every domain that matters for Europe's technological future. From photonics to advanced manufacturing, precision engineering, to cryogenics, nanotechnology, and quantum-proof ICT, just to name a few. And let me assure you today, these aren't just buzzwords. Through, amongst others, the works already done under the Dutch National Growth Fund ET grant scheme, we can confidently say that these market segments will define industrial competitiveness in the years to come. And the technologies being developed for ET don't just stay in the lab, or deep underground for that matter. They will spill over into airspace, into semiconductors, into medical tech, clean energy, and far beyond. You can expect our report with preliminary findings regarding these market segments in the upcoming months. So let's talk about the location. The candidacy of the Euregio Meuse-Rhine, where the Netherlands, Belgium, and Germany meet, isn't just a convenient geography or central location in Europe. It's a cross-border innovation ecosystem, where top universities, R&D facilities, and industrial base is already mobilizing for the Einstein Telescope. With still more than 18 months before the site selection, we're seeing leading institutes like Maastricht University, RWTH Aachen, KU Leuven, NICEF, and others working hand in hand with industry. Facilities like ET Pathfinder in Maastricht and ET Cristal in Liège are already prototyping new enhanced technologies. Not in theory, but in real life as we speak today and in collaboration with industry. To be more precise, already more than 80 companies, that's 80 companies, from the Netherlands, Belgium and Germany are working on technological challenges for Einstein Telescope. In many cases, these companies work in consortia brought together by EMR business developers and are subsidized by national governments or EU-regional programs, further emphasizing the importance and the support ET has in the EMR region. And this is only the beginning, as future calls are being prepared, as there's a lot of work still to be done. So whether your company works in ultra-precision optics, in sensor development, in smart infrastructure, clean room technologies, data processing, or in construction or logistics, there will be an opportunity coming along sooner or later for you in this project. From the current preparatory phase as a candidate site, all the way till planning, construction, and eventually operations, every phase will offer different opportunities. Because one thing is certain, despite the immense work already being performed by these 80 companies and the 400 plus companies expressing their interest through our ecosystem mapping tools, this is a project that will need more builders, more integrators, more problem solvers, and more innovators. I believe by now the message should be clear. Einstein Telescope will be a moonshot for European science and for high-tech industry. But that's not all. Beside high-tech R&D is also going to be a launchpad for new business models, new supply chains, high-value services, and adjacent industries like leisure and hospitality. And the EMR has the ambition to lead, not just to participate. By connecting with industry early, by collaborating across borders, and by focusing on valorization from day one. Valorization of the Einstein Telescope means translating the scientific and technology advancements into societal and economic value. This includes fostering collaboration between academia, industry, and government to ensure that knowledge generated around ET leads to new applications, new spin-offs, scale-ups, and eventually regional growth. A cross-border expert committee for valorization and impact, supported by a dedicated team of business developers, ensures that valorization efforts not only contribute meaningfully to the realization of Einstein Telescope, but also aim to generate tangible economic and societal benefits for partners involved. And those benefits can go a long way. Just look at what happened with CERN in Switzerland. It didn't just give us the Higgs boson, it gave us spin-offs in medical imaging, in network technology like the World Wide Web, but also cancer treatment and other real-life applications. ET could become such an engine for long-term economic resilience for the EMR region and for Europe as a whole. So if you are sitting behind your screen right now thinking, what's in it for us? My answer is simple. There's plenty. Whether you're an SME in a niche capability or a multinational with a global reach, Einstein Telescope will be a platform for collaborative innovation with the potential to drive value in both the science and the market. And for the moment to engage, that's now. The technologies are being developed, the partnerships are forming, and the companies that step in early will be the ones shaping the standards, the solutions, and the future applications. So as we talk about participation today with our guests, remember this: gravitational waves sparking this adventure may have come from space, but the real force behind the Einstein Telescope, the one that will carry it forward, will be you, the businesses, the engineers, the technologists, and all other partners who will make this bold vision a European reality. So don't go anywhere, because this conversation is just getting started. Coming up next, we'll hear how our three experts got involved and what they are doing on innovative welding technologies, silicon suspension, and vibration isolation at the sub-picometer scale. I can't wait to hear from them, so let's get right into it. Right. So you've heard already why we are here today. And for everybody who's watching, please make sure to give us all your questions through the comment section. If you're not able to see the comment section, please refresh your page, because there might be a small delay there. And with that said, we'll move on to our first guest. Our first guest is Marion Purio, Project Manager in Digitization and Smart Data at FAF Aachen, with a PhD from the Welding and Joining Institute from RWTH Aachen and a background in digital technology and computer science. Marion has been working in the BeamPipes 4ET project and brings valuable insights into the challenges of welding 130 kilometers of vacuum piping in tunnels 250 meters underground. Marion, welcome. It's great to have you here.
Thank you.
130 kilometers of vacuum tubes. That sounds like no small ask. Before you take us along in the world of these vacuum tubes and the welding technologies required, can you please tell us a bit more on how you got involved in the Einstein Telescope?
Yes, that was about 4 or 5 years ago. We had an online meeting with our regional business development agency in Aachen, AGIT, and we were just talking about this and that and upcoming projects, and she asked us if we have ever heard about the Einstein Telescope, and I decided to Google my missing knowledge about that, because I haven't heard anything about that 5 years ago. And while she was explaining what are the possibilities, I read an article online, and I said, wow, yeah, we're in. Yeah. That confused a bit the woman from Agit and my boss, but here we are.
So you were enthusiastic from the start?
Yes.
Did you already know from the start how big or how unique the requirements would be?
Not really, no. So I read that Wikipedia article, and I got an impression how big the project is and how important the project is, but I had really no idea how many people are involved and how many companies are involved and technologies and so on. So no.
Okay, so we'll hear more about that in your presentation later. There's also a sizable effort, not just in work you're doing, but also in financial contribution that the companies are making to make this a success. Is this an investment for the future, or are you already seeing benefits from working on this project in your current assignments or orders?
Yeah, what we are seeing is that we are more visible. So we are a small company, and we are not that well known outside of our location of NRW or Germany. And so yes, we are seeing that we are a bit more known. But it's also an invest in the future, because what we wanted to work on, the welding technology, can also be used in other fields of technology or production environments.
All right, cool. I'm sure that we'll be fine with that exposure after this webinar. Can I ask you to move to the presentation desk and let us see everything you've been doing in the project BeamPipes 4ET?
Of course, yeah.
Thank you.
Thank you, and a warm welcome from me too. Thanks for watching my presentation today. Let's start with a short introduction about FEF. So we are a small company with about 15 people who are all deeply rooted in the welding technology. And we see ourselves as a service provider for all kinds of joining technologies, especially for welding. So you may now ask, okay, what does that mean? What kind of services do you need for welding technology? So let me give you a short overview of what we are doing. We are there from the start to the end of a welding process lifetime. So if you have a new application, new product, and you are unsure which welding process is suitable for that, we can help also to implement the process in your existing production. But also if you have an established process and something has changed or something goes wrong, we offer a service to come to the plant and see where the error might be. So we do this for all kinds of welding processes, not just the well-known arc welding processes, but also beam processes or the so-called cold technologies like ultrasonic welding. And we are not specialized on one specific material. Everything what might be metal would be fine. So kind of aluminium, copper, steel, but also material mixes. But let's come to the Einstein Telescope now. So we started, I just told that some years ago, with an innovation voucher from ET to SMEs. And you see some numbers here and some have been updated in between, but the task was to find a way of a continuous production of the 120 kilometers of beam pipes, which takes place underground, under the earth, directly in the tunnels. And we had 4 project partners and a project duration of 7 months, so it was a short project. Funded with about 50,000 euros. And now you may ask, okay, that's nice, but what for? Why do you care about that? And where do you get the funding from? So let me give you a short example of a calculation, a simple calculation. If you want to do 120 kilometers and you do it classically in a 20-meter section, you need at least 6,000 of them. And 6,000 sections means producing them, transporting them, placing them in the tunnels, and of course joining them also. And hard for me to say, but every weld is a potential weak spot in the whole system. So the task was to reduce the effort logistically, but also financial effort, and improve quality by seeing if we can reduce welds. And therefore we came up with the idea of making longer sections of 500 meters. Then you need 240, what's way less. And if you see here that what might be a coil of 50 ton, then this would be the same as 25 of these 20-meter sections. And you can see the weight is the same, but the volume you have to transport is way less. So we had some ideas on how to weld, where to weld, and of course which process we can use, and decided to do an innovative approach of a laser beam in a mobile vacuum system. This has some advantages, for example, to reduce pollution, to reduce the energy input, to stabilize the process. But the thing you can see here on the image is something you can find in research environments, like the Welding and Joining Institute, but not really in production. So there were some challenges, to fit the shape of the mobile vacuum head, to see if we can really realize this under production environments, and of course with the desired welding speed also. But in the end of the study, we came up with a good feeling that this will work out. And then someone came up and said, okay, then prove it. And so Beam Pipes for ET was born, our follow-up project. And in Beam Pipes for ET, our task is now to prove that the concept can work, to build production and an automatic welding process, which can then weld several meters. Goal is to weld 500 meters, but here several meters of this ultra-high vacuum tubes under real production environment conditions. Yeah, and last but not least, not to mention, not to forget our project partners, that this wouldn't be possible if we would try to do it alone. So we have some good partners, some glorious partners, starting with Aachen University, who's in lead here, with Werkhuysen Hengelhoff, with departments from the University of Hasselt and Antwerp, SBE and Aparam, which make that possible. And we are half in between the project, in the first half at the moment. But the good news is that we still think that this will work out. And we are looking to the future, see if our contribution can help building this Einstein Telescope. So, that's from my side. And please feel free to ask questions.
Yeah, thank you very much, Marion. I just got a quick update from the tech team. If the chat is still not working for you, please refresh your screen. It should all be up and running. Some viewers already reported it's working. So if you have any questions for Marion, please refresh your browser quickly, and then you should be back with us with a functioning chat function. So let's get to some questions. I'll get them in a minute. So maybe we start with mentioning you do this with your partners. It's a nice set of tri-national. I saw some Belgian partners, German, Dutch. So it really shows the strength of the EMR region. It's done under Interreg subsidy, you said. Yeah. So that's a very nice picture of how it went from a voucher in ET to SME, growing into this project where you're actually going to build a prototype. Will that prototype be tested as well?
Of course, yeah, of course. So we test from the welding perspective. We already test the welds we do. So there we are working with Hasselt very closely. They test if you can bend the weld, what happens in between, if you have pores in between. Of course, one of the main requirement is that it's gas proof, because it has to work under very tight vacuum conditions.
Absolutely. All right. So are there any results that you can already share so far? You mentioned you're in the middle of your project. How is it going so far?
Good. So we made some weld tests, but we slightly changed the conditions in between. So we started with a 4 millimeter sheet thickness, and now we are down to 1.5 millimeters. So at the moment we are welding them, and they will be tested, of course, also, and see how it's going. But it seems to be working well. Yeah. Oh,
that sounds good. That must be a huge cost benefit as well, reducing the amount of material.
Yes, of course, material is one of the cost drivers. Yeah, in the project, of course, not in our project, but it might be a large difference if you have 120 kilometers and you have 4 millimeters or 1.5. Yeah.
All right, sounds good. We're gonna. There's another question coming in. Is inline cleaning also taken into consideration?
It is, it is, but not really within our project. So that might be a requirement. So since we weld in a mobile vacuum or in a vacuum system, a lot of dirt is already sucked away from the vacuum system, so we have less pollution. but there will be pollution, and we have to see how clean we can go. But I think we need an inline cleaning, yeah.
Okay. Yeah, we definitely do in the end, of course. Thank you. Last question. Do you see this technology land somewhere else? You mentioned conventional methods. This would take 16 and a half years. Do you see this technology then also landing in other fields, or?
Yeah, it can be used for any kind of pipeline building, for example. So if you have the possibility to make your pipeline quasi continuous in the field and you don't have to transport it, it might also be an advantage for you. Yeah.
Mm-hmm.
So.
All right. Cool. Thank you. We'll see if more questions come in, and then we'll get back to you later on, because people got access to the chat, I think, a bit late, but we'll have plenty of time. I'll come back to you if needed in the end. So then we'll move on to our next speaker, who is joining us digitally. That's Remy Wieland. He's co-founder and Chief Technology Officer of Wieland UPMT. Wieland develops ultra-high machining and replication technologies that are directly relevant to some of the core technologies needed for the Einstein Telescope. Welcome, Remy, and thank you for making time for us through this online link. When I first read the description of the ET Fibers project, I was not quite sure I read it correctly. It said you're developing silicon fibers with a cross-section of just 3 millimeters, but able to suspend silicon mirrors weighing up to 100 kilograms. And to make it even more fascinating, it's done at close to the absolute zero temperature. I guess my question here is, how unique are these requirements?
Yes, these requirements may sound crazy, but it is real. So it is needed because the Einstein Telescope will need to function at close to 0 Kelvin. And the mirrors of the telescope need to be isolated from vibrations. So that's why they will be suspended by these very thin fibers.
All right, cool. So I'm looking forward to hear more on that in a second. But first, I also noticed Wieland is still a family-owned, 100% family-owned business. You have 8 to 9 employees. So how did a small SME like yours got involved in such a big project as Einstein Telescope?
Yes, we are a very small company, but we got involved in this project because we are very much a solution-oriented company. We have developed technologies in the field of ultra-precision machining and of molding of polymer optics. And so we like to think out of the box and develop new techniques, new technologies. And here that's what we are doing. The fabrication, the manufacturing of these fibers really requires a new mindset, and that's what we are doing.
All right. So then I'm going to ask our technical team to start your presentation, and you can tell us a lot more about what that means, thinking outside of the box with silicon fibers.
Okay. So thank you. I'm Remy Wieland. I'm managing partner and CTO of our company called Wieland UPMT. We are, I will tell you today about what we can do for the production of these silicon fibers or silicon joints. So, next slide. So we are a family-owned company, like you said. We are located in Liège, in Belgium, very close to, we hope, the future site of the Einstein Telescope. We have a very wide customer base, and we are specialized in the manufacturing of optics by diamond machining processes and replication processes such as injection and compression molding of polymers. Next slide. Right now, we offer 3 types of services to our customers. We offer the machining of masters or inserts, and more specifically, masters with lens arrays. We have developed proprietary technology in this field, patented technology that allows us to diamond turn such masters. We also offer replication services. So in this case, we will use internally made masters or inserts made by diamond machining, and then copy the mold using polymer injection or compression molding. Finally, we offer more general diamond machining services, mostly for the space industry or defense or the like. Next slide. So by diamond machining, we can process different materials. First are the ductile non-ferrous metals, such as copper, beryllium, brass, aluminum, nickel, phosphorus. Of course, for some prototyping, we can also diamond machine directly without replication some polymers, such as PMMA. But a number of crystals are also diamond machinable, such as zinc selenide, germanium, magnesium fluoride, calcium fluoride, and silicon. So these crystals can be machined in a ductile regime under the right conditions. In terms of geometries, we can process spherical, aspherical, but also free-form surfaces. So we're not just limited to rotational symmetric shapes, but freeforms are also possible. To give you an idea about the accuracy of this diamond machining process, shape accuracies are in the range of 100 nanometer peak to valley, and we achieve optical surface qualities by this process without the need for post-polishing. So we achieve roughness values in the range of 2 nanometer. Next slide. This process is very has been used for example, here I show our space heritage, where we have used this process for metal mirrors, flight mirrors, whether it is off-axis aspherical mirrors, can be very light-weighted mirrors in aluminum and nickel, etc. Next slide. Now, within the scope of the Einstein Telescope, what can we do? What can we offer? Well, you can see here in the image the large silicon mirror. It will need to be suspended by these fibers. So it needs to be suspended by fibers because the mirror must be vibration isolated. And of course, the fibers must be as thin as possible to act as flexures. At the same time, and that is a contradicting requirement, the fibers must be conductive, such as to cool down the mirror. there aren't many materials that can satisfy the requirements that but silicon is one of them. So silicon has good thermal conductivity, close to the absolute zero, and also has close to 0 CTE at this temperature. At the end, you see that the fibers will need to be very long, close to 600 millimeters in length. So there is a huge challenge in making these fibers, which with this small cross section in such a very brittle material like silicon. Next slide. We have done some tests, machining tests of these fibers already. We did this for NICEF. The objective of the project at that time was to demonstrate that we can thin down a fiber that is originally 13 millimeter in diameter down to 3 millimeters in diameter over a length of about 45 millimeter. And that we could do this also with a very good surface quality, because we don't want to create cracks in the material that would later lead to the fiber breaking. So we developed a special tooling and special diamond turning approach to achieve this, and I can show some results in the next slide. So here you see the one such fiber that we made. We measured the roughness values that we were able to achieve in the thinnest section, and we achieved there between 20 and 200 nanometer RA, depending on where on the fiber. There's some places where we're at 20 nanometer. Next slide. We did the second iteration for NICEF, another design where you see that at the end of the fiber on the left side is a 45-degree cone, let's say 90-degree cone. On the other side, the end of the fiber is flat. This may be needed for the attachment of the fiber to the mirror and to the frame. So we demonstrated here that this design is also feasible. And we achieved even lower roughness values here at the lowest at 10 nanometer RA. Of course, we're not yet at the ultimate roughness values that we would like to achieve. So there is room for improvement. But what we have to remember from these tests is that the origin of the degraded roughness lies in the orientation of the silicon crystal, the tooling design, the flexure stiffness, of course, also the tool wear, silicon being a material that's very hard to cut. There's a lot of wear, and the surface slope angle variations. Next slide. We have entered and been awarded a funding for to further develop this capability of manufacturing these fibers. And so we have, as a consortium of 4, we have obtained the funding starting in September of this year. The participants are the University of Liège, that will design the fibers, simulate and integrate them. The University of Leuven, that will do the characterization of the fibers. There's the company Lasea for the laser post-polishing of the fibers. And finally, Wieland's UPMT that will integrate laser-assisted diamond machining of the silicon fibers. So this is a new approach which we have not used yet in the tests I showed before. Next slide. This was my presentation. Thank you.
Thank you, Remy. And let's have a look at the questions from the chat. I must say, from all the things in the Einstein Telescope, these fibers still like blow my mind. What kind of precision and strength and everything you can achieve. And laser-assisted cutting, it just really sparks my imagination. So very nice to see. And congratulations also on the ET Fibers project. It's a testament, I think, to the preliminary work you've done, and the continuation is really good to see. Let's see, there's some questions coming in. How did, let me see this question. You mentioned NICAF as a knowledge partner. How did you connect with NICAF?
Yeah, good question. I think NICAF approached us. They knew that we were active in diamond machining. So we did not approach NICAF. They came to us, and they came to us knowing that we had this capability of diamond machining, and also the will to develop new approaches, new technologies.
Okay. And can you tell us a bit how then the continuation of ET Fibers came to life?
Yes, this was the ET Fibers project is pretty much for us the continuity, let's say, of these tests. It is also for the University of Liège that has already, of course, been involved very much into the project, having done this demonstrator. So for these two, for us and the University of Liège, it's the ET Fibers is the continuity of the work that we have been doing before.
Okay, you mentioned Liège. Does that mean you're testing your fibers at ET Kristal?
Yes, that's the goal.
Okay. And is that so? That's an important and useful facility for you already to test these fibers in a real life setting.
Exactly. Yes.
All right. Cool to hear. Then last question that I see coming in now is: do you see any opportunities for your own strategy or application in current business for this technology?
Yes, of course. This was a, let's say, a condition for us to step into such a project. We want to have use for this technology also in other fields, and of course in the field that we are already active in, which is optics. So laser-assisted diamond machining is a process that is very interesting for the manufacturing of optical parts also, because there are a lot of optical parts now being done also in silicon to replace, for example, germanium optics, because germanium is becoming more rare and very expensive material. So there is a transition in optics towards silicon. So if we develop this know-how in diamond machining of silicon for fibers, we're going to use it also for optics.
All right. Then one final question. Are you also in contact with the University of Glasgow? Because apparently in the chat they're discussing that they're also working on this topic.
Not yet. No, we're not.
Right. Might be
Maybe we
interesting
should
to discuss. Synergy is coming from every
yes,
from every angle, so maybe it's nice. All right, thank you. We'll keep an eye on the chat and maybe we'll circle back to you. But thanks for the presentation and very insightful. And with that, we'll move on to our third guest back at the table with a background in mechatronic engineering. Jochem Klaassen co-founded Lionite in 2019 and is currently leading the company as their CEO. Within the Senvidet project, Lionite develops ultra-sensitive, low-frequency sensors for vibration isolation in the Einstein Telescope. By combining expertise in optomechanics, signal processing, and precise engineering, the project aims to enable measurement at the sub-nanometer or even sub-picometer scale. Again, blows my mind, which is crucial for the observatory stability and performance. Welcome, Jochem. In an earlier conversation we had, you told me Lionite was already for a while interested in the Einstein Telescope before you joined. Can you tell us a bit why you were so interested in Einstein Telescope?
Of course, yeah. So we all at Lionite have a deep fascination with physics. So from the nature of this moonshot project, we were already interested. And at the time, we were working on an interferometric sensor that we thought could align with developments in Einstein. So from the moment we heard about it, we were hooked. Yeah.
Great to hear and share the enthusiasm. In some of the presentations we've seen, we heard a lot of different funding schemes, ET to SME, Interreg, EMR, regional funds from our partners in Wallonia. You, however, applied to the Dutch Einstein Telescope R&D grant scheme, and in particular to the call around optics. Why did you go for this option?
So it's not an option we, beeline for from the start. We joined the early talks during, the initial conversation with the scientists and the challenge. And it's at these talks that we really, had a hunch that our sensor and our developments could align. And meeting the right parties there and getting interest in our technology kind of gave us the boost, like, oh, this does align, let's go for it. Yeah.
So it really happened during sessions where you came together.
Exactly.
Okay, that's great to hear. And I assume you then didn't apply by yourself.
No. So we have an amazing consortium, and I think it's true for a lot of the challenges in Einstein. You need each other. Like Lionite doesn't have all the answers. So no, we met a large part of our partners at these meetups, and I can say we're very happy with the project. We've got some amazing partners, all with amazing contributions. So exactly, teamwork makes the dream work.
All right, awesome. Then I'm going to ask you to move to the presentation desk and tell us about your dream.
Yeah, very good. Right. Thank you, Jurek, for the introduction. I am Jochem Klaassen, CEO of Lionite and coordinator of Project Senvidet. Thank you for joining me today in discussing our sensor developments for vibration isolation technology in Einstein Telescope. So I want to begin with a bit of background about ET itself. And you may be aware that Einstein Telescope is an attempt at extending the measurement range of gravitational waves to the lower frequencies. Because in the 3 to 20 hertz frequency band, there's a lot of interesting stuff happening, gravitationally speaking. But if you want to reach this performance, it's actually very, very challenging. In the graph on screen, you see the, comparison between the required performance for Einstein Telescope and what's currently achieved in the second generation gravitational wave observatories. And you can see that once you move down to the lower frequencies, you're met with this barrier of low frequency noise that needs to be overcome before you're able to make this amazing instrument work. So about our project, what are we doing to aid in this feat? So Senvidet, or Sensor Engineering for Noise and Vibration Isolation and Damping in Einstein Telescope, rolls off the tongue just like that. is a project where we're working on a new generation of ultra-low noise, low-frequency sensors to make vibration isolation possible to the level that needs to be met. We're doing it with 7 partners, a bit more on that later. We got a time of 3 years and a budget of 1.7 million euros to make this work. So zooming in a little bit more, first of all, our partner Somni Solutions is working on a fiber optic seismometer to measure at this low noise and low frequencies the seismic activity right next to the vibration isolation systems. InnoSeis is working on a beam balance tilt sensor that's needed to track, say, the swaying motion of the vibration systems. Quantified Air is working on a sub-picometer interferometer. This is to be integrated at pretty much the last stage of active vibration isolation in the stage, right before the suspended mirror. And Lionite, us, we're working on a high dynamic range laser interferometer that operates between 2 vibration isolation stages to suppress the relative motion between them. So joining our consortium is NICEF, the Dutch Institute for Subatomic Physics. They're really helping us navigate the requirements and the challenge with regards to Einstein Telescope, and they can tell us what's useful for them. VSL, the Dutch National Metrology Institute, joins because the level of sensor performance we're trying to reach doesn't have a standard or a reference yet in the world, and this is very important when you want to verify sensor performance. And DEMCOM from a systems engineering perspective, because coordinating and navigating this whole system of requirements is a challenge in and of its own. A bit about us, Lionite. We're a small company, also 10 people, located in Delft, the Netherlands. And Lionite develops semi-custom electronic systems based on our proven IP building blocks. We do hardware and software development in this method, and we also supply services on production, testing, and support, which means that clients come to us with a question and need for customized systems for their product, for their system, and we're able to use our IP building blocks to, say, build the majority of the solution, so you only need real customization on the levels that are specific to the project. And we do this all based on our expertise in high-speed electronics, analog instrumentation, and electro-optics, which is our link to the Einstein Telescope. We generally work in a contract engineering fashion, but we also have our own system sensor developments, and our laser interferometer is a good example of this. So building this up in these IP building blocks I just mentioned, it looks something like this. So this is stuff we've already mastered, we can implement. But of course, this part is the real low noise, low frequency part of the system. And of course, we don't have this lying around. This is really for us the focus of our R&D inside this project. And to give you an idea, on this graph, you can read the required sensitivity of our sensor. And on the left, it says, 10 to the minus 10, 10 to the minus 11 meter per root hertz at very, very low frequencies. So very challenging. We're now at the stage where we're gonna perform our first noise characterization. So follow us on LinkedIn to see how we're doing. Now a bit about our experience being part of CENVIDET and being part of this, let's say, ecosystem Einstein Telescope. I want to start with some takeaways, some lessons learned from our process of creating a project. And that's that the initial discussions with scientists and industry are super important. So the scientists working on Einstein Telescope, they've got a real good idea of the nature of their challenge, but they don't necessarily have the answers. If they would, they wouldn't be calling on industry. So these early talks are very important to figure out where perhaps the interests overlap a bit, where can industry collaborate. And something challenging here, but very important, is to define valuable goals towards aiding Einstein Telescope as a whole, but something that's at the same time realistic, because like Jorik mentioned, it really is a moonshot project. So key takeaways I want to share with you here is to really be present at the early talks. It's better to be interested and attend and then figure out like, oh, maybe it doesn't align, rather than miss it, because for us, we went in it with an open view and we really found our way there. And Einstein Telescope, it contains so many challenges in need of a solution. It's also difficult for the scientists or the development agencies to really pinpoint where you might be needed. So that will probably ask some initiative on your part to really propose the solutions you might have. Lastly, the value we see in participation. So we're very happy, very positive to be able to be part of this project. We're developing new technology on a very, very high level in a very powerful ecosystem, working together with NICEF and VSL. The expertise they have is really amazing, and the same goes for their testing facilities. We're really connecting to fundamental research, and if you're like me, beforehand I thought, oh, these fundamental scientists are just running around with their leptons and quarks, and it's too far away from being relevant to industry. But in their experiments and in their designs, they're facing a lot of the similar challenges we are in industry. So it's really quite valuable to go out there and talk to them. Because we're in this ecosystem for us, really focused around low frequency performance, sensing, actuating, we're constantly being approached with new questions and new opportunities for this technology we're working on. And finally, of course, it feels really good to contribute to something bigger, an amazing leap forward like this. So everyone in Lionite that gets to work on this is very happy to be doing so. And that's it. Thank you.
Awesome. Thank you, Jochem. Please come back to the table and we'll have a look at the questions coming from the audience. Very cool to see also the value you already see in participating in such a project, and a testament to what you're doing. Let's see what came in from the chat. So first question, the challenge you're working on together with the consortium is pretty fundamental and very specific. How are you ensuring that this integrates well in a big complex instrument like the Einstein Telescope?
That is a very good question, and it's very, very difficult to guarantee something like this. The first part of our project is really centered around, let's say, identifying the weak spots that currently limit the performance of Einstein Telescope, which again is very difficult. NICEF is working very hard on this, collaborating with DEMCON to identify this. I guess I can answer the question by saying we're certain that we identify weak spots that need solving. We're not certain that by eliminating these weak spots, the whole system works. That's also slightly out of scope for our project, but very difficult to do, but that's our approach.
All right, sounds good. You also mentioned, or you showed at least some slides from ET Pathfinder. Does that mean you're also testing there?
Not yet. No. It's an ideal testing location for us, but so far the facilities at NICEF itself, including the multi-sus system they have there, seem to be the first logical step. But we are talking to people from ET Pathfinder, so hopefully towards the end of our 3 years, we'll have something working there.
All right, cool. And the 3 years is a nice horizon?
Yes, I think so. So don't expect all of the sensor challenges to be finished in 3 years, but we're very confident that we're making good steps in solving them and getting closer to, right? So our project is not really tasked with solve the issues like this, but bring us closer to that horizon. And I think we're going to get very far in these 3 years.
One step at a time.
Exactly.
All right, cool. Thank you very much. Maybe to close off with a question for all three of you, because I think the presentations you gave all mentioned knowledge institutions, universities and industry partners working together. Can you share a bit if you're doing that more often or how you're experiencing that so far? Starting with Marion.
Yes, we are working in publicly funded projects for some time, but since we are a smaller company, so we have to see that we get our daily business done also. But we have never before worked with interregional partners together, so that was a novum here. Yeah.
All right.
And it's really great.
Jochem?
So similar answer. And being located in Delft, we already work together quite a lot with TU Delft and VSL because they're located in our proximity. Einstein Telescope for us really was the intro to NICEF. That's a research institute we did not collaborate with before, and that has been very, very pleasant. So that's new, but otherwise, of course, located in Delft, you kind of have to.
Cool. Anything from Remy? I expect you're still in there.
Yes, I'm there.
Cool.
So yeah, we for us it's the first time that we are in a publicly funded project with other regional partners. We have experienced publicly funded projects before, but not in a consortium like this with other universities, for example, involved. Now we're used to work with such institutes, but more as customers. Yeah.
All right, cool. So then I see one more question coming in. You're all obviously with the work you're doing, helping the realization of Einstein Telescope, making it a reality. But you're also helping the EMR bid because you're all situated and located within in our EMR region, or at least in our countries. Is that something you find important, that the Einstein Telescope will land close to your base?
Yeah, yeah, I think so. So it's not even here yet, and you already see that it's making quite a big impact, especially in seeing everybody who's already involved. And I think you get 3 countries instead of 1, and it's very closely located to other industrial areas. So it would definitely mean that I can drive down to Einstein Telescope more often, which is worth something to me. And I think it does provide a lot of value to us and similar companies. So for sure.
Mm-hmm. Anything to add from our guest?
Same here. So I lived directly to the Dutch border my whole life, basically, and it would be so good to have such a huge project nearby, and I think it would help both the industries and the universities and research institutes. So let's press thumbs.
Yes,
that it will work
out.
out.
All right. So that concludes the questions for now. If you still have any questions, viewers at home, please put them in the chat. Also, if you have any topics for the future, please put them in there. We're happy to see how we can accommodate those, and then we'll move on. Yeah, we'll move on to the wrap-up, because we're coming up to the end of this session, the very first in our series of Einstein Telescope industry webinars. I want to extend a sincere thank you to our speakers for sharing their time, their insights and expertise. Your perspective has really set the tone for what we hope to be an ongoing and productive conversation between scientific community and the many industries that will help make this groundbreaking project coming to life. Thank you also to you guys, our viewers, for joining and for the engaging questions you asked. Whether you represent a multinational, a SME, a research institute, or a regional development agency, your engagement is much appreciated and vital for the success of ET. And remember, this was just the beginning. In the coming months, we'll continue this webinar series, where we'll share deep dives into the key technologies and opportunities for future collaboration. But we will also be attending various trade fairs in the Netherlands, Belgium, and Germany if you want to meet us live. We'll hope to see you again and help build the bridge between science and industry. If you'd like to stay informed about upcoming sessions, follow-up materials, or collaboration opportunities, please reach out to us directly or register in our ecosystem tool. You can find all the relevant information on the company section of our website, or you just scan the QR code on your screen right now. On behalf of the entire team behind this webinar, our tri-national partners, and the entire Einstein Telescope community, I'd like to thank you again for being here, and we look forward to seeing you in October for the second webinar. Take care and goodbye for now.